hard. All right. All right. Waiting for everyone to file in. Welcome, everyone. It's a pleasant, nice autumn day here in Austin, Texas. Meaning it's not 95 like it was yesterday. All right. Looks like everybody's filed in. All right, let's hurry. Let's get this thing going. Welcome, everyone. Hey, welcome to the DesignSafe. I think this is the second webinar that we're doing for this semester. So it's great to have everyone here. These are always kind of a special deal to me because these are our Dataset award winner webinars, and so I'm really looking forward to this. First off, if you hadn't had a chance yet, please check out DesignSafe's news site. There's some information regarding Hurricane Helene and the NSF-funded recon scientists that actually retrieved the data for us, and there's a really good story on there about that. And of course, if you haven't heard already, DesignSafe is now a core trusted seal for a data repository, which is a great deal. There's not that many science gateways that have that core trust seal on them. So please feel free to read about that. Essentially, we're talking about how easy it is for you to bring your data into our system, how to curate it, how to secure it, and all that fun stuff. So if you have a chance, please check that out. All right. Also, regarding these webinars, we would love your feedback. So there's a QR code in there. So if you could take a little bit, scan that, take a survey at the end of today's webinar, it kind of gives us a great feeling on directions we should take these webinars, what interests you have, and basically how to get those interests into a presentable material and show off to the community. Also, if anybody has a data set or something really cool that they've been doing on DesignSafe or with DesignSafe, feel free to let us know. And we'd love the rest of the community to know as well. And this is one of the best ways to outreach the DesignSafe community. So please go ahead and scan that, give us your feedback, and we would love to use that to build on for future webinars. So with that, let me introduce the topic for today, and then I'll hand it off to Scott Brandenburg to introduce today's speaker. So today, like I said, today is one of the 2024 Dataset Award winners. We're looking at the peak ground acceleration and other ground motion intensity measures at liquefaction field case history sites. So this is essentially going to discuss a DesignSafe data set of ground motion intensity measures that have been computed at liquefaction sites, historic sites, based on consistent approach that address the limitations of legacy PGAs. And so this framework is used in the study that computes IMs at liquefaction sites from the Next Generation Liquefaction database using the Kriging interpolation and spatial correlation models developed using Bayesian inference. Ground motion models and data from the Next Generation Attenuation projects and other technical literature are used to facilitate these calculations. So with that, let me introduce you to Scott Brandenburg, who is one of the co-PIs on DesignSafe, and also has very intimate knowledge of this data set and has worked with our speaker today. So Scott, let me hand it off to you.
All right, thanks a lot, Charlie. So it's my pleasure to introduce Professor Renman Patel. Renman did his PhD at UC Davis, and I've known him since that time. After he graduated from UC Davis, he went on to UCLA to do a short postdoc. And I worked with him closely during that time, where the work that he's presenting today was conducted during that time. And he's now an assistant professor at University of Nevada, Reno. Some of you may be wondering, like, how did a dataset award go to a co-PI of DesignSafe? So I can assure you that I was not involved at all in the selection. Renman really did the work and wrote the proposal, and he's the one doing the presenting today. So Renman, thanks for coming, and I'll hand it off to you to share your screen and get us going.
Thank you, Scott, for that kind introduction. Let's see if I can figure this out. Okay, let me know if you can see the full screen and the laser, the pointer in there.
Yeah, it looks good.
Yeah, you look great.
Okay, perfect. Thank you. Thank you, Scott, again for the introduction, and good afternoon, everyone. First off, I'd like to thank DesignSafe for the recognition of our work and also for providing the resources and the platform for allowing researchers like us to share our results, products, and also calculation methods. So secondly, I'd like to thank Scott and the DesignSafe team behind this webinar for the organization. I am very excited to be here today about the award and also happy to be with you all. So without further ado, let's go into the presentation. The title of my talk today is Peak Ground Accelerations and Other Ground Motion Intensity Measures at Liquefaction Case History Sites. And the reason why the second line is in a different color is because for this presentation, I will mostly or entirely focus on peak ground accelerations, PGA from now on, but the methods, the strategy, data collection, and so on are equally applicable to the other ground motion intensity measures that we have in our dataset that I will show you briefly at the end. So first off, I'd like to acknowledge the team. As Scott already mentioned, I work on this project with Scott Brandenburg and John Stewart, both professors at UCLA. A wonderful time, had a lot of fun, and well, just wanted to let you all know this is a team effort, but I am just here presenting our results. You know, as most geotech talks have some cool liquefaction pictures, and this is not going to be the exception. The motivation for this work was soil liquefaction, right? I have here a couple of pictures. On the left, one taken in Peru after the 2007 Pisco earthquake. You see a lot of settlements there. On the right, some picture, a picture from a more recent event, a 2023 Turkish earthquake sequence. And so liquefaction, very important phenomena for geotechnical earthquake engineering. And the most common approach for assessing soil liquefaction is using liquefaction triggering models. These are very simple. This is why they are widely used. Basically, we rely on a definition of a factor of safety, which is equal to the resistance, without going into details, just the resistance over the demand. The resistance depends on soil conditions, whether the soil is loose or dense, there's some pine contents, and so on. And the demand, which is the focus of this presentation, mostly depends on ground motion intensity measures. Traditionally, the peak ground acceleration, or PGA, has been dominantly used in liquefaction triggering models. And so most people are probably familiar with this plot. Okay, what I am showing here is one of the data sets in the circles and one of the models for liquefaction triggering, or a couple of them actually. These are proposed by Professors Boulanger and Idris. If I simplify a little bit the axis, basically what we have in the horizontal axis is the resistance, the soil resistance, and in the vertical axis, the seismic demand. And so many researchers have focused on developing these models, which are basically this curve that somewhat divide the cases where liquefaction was observed in the field. Those are these red circles on the upper left, from the cases where liquefaction was not observed. And these are the open circles at the bottom on the right. Now, this separation is not very clean, right? There are some reds under the line and some empty circles above the line and so on. But one of the factors that really impacts where these circles are placed is the PGA, because the seismic demand defines how high in this vertical axis these case histories are. And so I've been talking about case histories. Each one of these circles represents a case history, okay? And so what I'm saying is basically we have these models, we use them to assess liquefaction triggering, and these models depend significantly on the PGA value assigned to a given case history, okay? So if we look at the databases, these PGAs can vary in how they were estimated For example, for this case history of the 1989 Loma Prieta earthquake, the Miller Farm site, there are 6 different values of PGAs that I found in a database by Shetin et al. You can see in the top, if we trust intensity shaking maps, the PGA at this site can be estimated at 0.5 or 25 to 0.5. If we rely on ground response analysis or site response analysis, the value is 0.41 and so on, right? There are different techniques and methods used. And so what I will do now is highlight some keywords in all of these methods. We have maps, we have ground response analysis, ground motion models, some recordings. Sometimes we are lucky to have some recording near the site of interest. And so in some cases, we also have judgment, right? Particularly if there is no recording and there are no data available. And so there is a wide range of values if we look at all of these PGAs, right? So if we were to select a PGA for this site, that value can be as low as 0.25 and as high as 0.65. And so then these liquefaction case history data sets are mixing a bunch of these different methods, which might lead to problems in the, or just inconsistencies in the liquefaction triggering models. So that is the motivation. There are inconsistencies in the PGAs from different estimation methods, and we can leverage or use recent developments for revisiting the PGAs at liquefaction history sites. And so that's what we did, right? More than this, but mostly 3. First off, we have databases that perhaps some of those researchers that estimated the PGA for legacy cases did not have available at the time. We have the Next Generation Attenuation models, the Next Generation Liquefaction database, ground motion models, as I said, NGA West 2, NGA SAP, NGA East. So we have a lot of ground motion data supporting these models, or at least more than the data a lot of the researchers had back at the time. And we have methods and tools. We have some spatial correlation functional forms and Python implementations, libraries, and all of these allow us to revisit these values, right? So this somewhat shows also the evolution of our techniques. Right? In our field, we now have more data, more tools, perhaps more informed models, right? So it just makes sense that we have the tools now to revisit these values. And so with that, this is the plan for today. For this talk, I covered the motivation. What I will do now is show you some of those legacy PGAs to emphasize why we really need to do this project. We need to revisit these values. I will focus on the pitfalls of some of these methods. Then I will show you the methodology that we use, the consistent methodology for estimating PGAs. I will take a couple of minutes to discuss the spatial correlation models, because even though it was just one step in our methodology, we really spent a lot of time working on these models. And we have some results to show there. I will then compare our estimates with the legacy PGA values. I will talk a little bit about the data set on DesignSafe, and I will finish the presentation with some concluding or final remarks. Okay, so let's do it. Legacy PGAs. So NGL, the Next Generation Liquefaction, currently has near 600 or 560 liquefaction case histories. And after looking at all of those, we grouped all of the methods used to estimate PGAs in these 7 categories. Okay, some of them were recorded at the site or co-located. The second one is interpolated from nearby stations. And this is in a different color because it's basically the same methodology that we are using, and I will present you in a moment. The other method is near real-time post-earthquake maps. The next one is ground response analysis recorded at the nearest seismic station. Okay, even though it says the nearest seismic station, sometimes that is not that near, it's a little bit far, okay? Estimated from ground motion models and based on judgment. And we sort these categories with these numbers based on our estimate of the accuracy. We estimate that from top to bottom, we will have more to less accuracy on that estimated PGA. Okay, just to mention here, it is a little bit unclear to us how accurate ground response analysis can be, because there is a lot of dependency on the input ground motion, right? On the quality or the selection of that input ground motion. But we decided that number 4 is a good place for it. So now what I will do is spend a couple of minutes to discuss the first, the fourth, and the fifth methods. In the case of the first method, recorded at the site or co-located, one of the pitfalls can be that the PGA recorded at the liquefaction site might be affected by liquefaction, right? It's kind of expected. And so therefore, if the PGA is affected by liquefaction, that PGA cannot and should not be used for the liquefaction triggering model developments, right? Because the assumption of these models is, okay, let's take the PGA at that site in absence of liquefaction, which is a little bit of an abstract idea. But basically, if we have a recording at a site and we can tell, or we assess the recording and we see that it was affected by liquefaction, then it should not be used. And so as an example here, I have Professor Kramer has been working on this work, on this assessment or identification of liquefaction based on the recordings. And I have here a figure by Greenfield and Odener et al. And we can see, well, these researchers picked this time as the initialization of liquefaction, right? And so this is somewhat early in the record, or early during the earthquake. And everything else after this point is affected by liquefaction, right? We can clearly see here some dilation spikes that perhaps are exaggerating the PGA that we would get in absence of liquefaction, right? So that is the problem. So basically, for this study, we went through all of those cases and we removed the recordings that were affected by liquefaction, with a couple of exceptions. One of them is here. This is the recording at the Treasure Island of the Loma Prieta earthquake. And again, this is the time where liquefaction was identified. But if we compare this recording with all of the, let's say, neighboring stations, we see that the strong shaking, or the stronger part of the shaking, is before this liquefaction initialization. And so we decided that it was safe to use the PGA and PGV, peak ground velocity values, before this point of liquefaction, right? And that was representative of the PGA at that site, okay? So we tried to use the data that we have, and we made a couple of calls like this. Of course, we also work for cumulative absolute velocity and ARS intensity, and we did not use this record for those because those are cumulative ground motion intensity measures. I can elaborate on that at the end. So another method is method number 4, ground response analysis. And again, the accuracy of this method significantly depends on the input ground motion. Generally, a recorded outcropping motion is used. That might not always be available. But even for cases where there is a near outcropping recording, that is generally far enough that then the input motion is not representative of the incident wave at the site, right? So again, this is a little bit hard to assess, but there is this strong dependency. The other method is the nearest seismic station. And just to keep it short, basically path and side effects are missed. And as an example, I have here the non-tow sites, are the sites here shown in this red square. These are sites or liquefaction case history sites of the 1999 Chichi earthquake. And what happened in this case is that a value of 0.38 Gs PGA like this was recorded at this station right here. And so that PGA was assigned to all of the sites that were in Nantao. It's in the same city. But the problem is, as I said, that path and site effects are missed. And so for some of you that might be familiar with ground motion models, site and path and site are usually captured by just the distance to the fold. This is the joiner bore distance. And the VS30 for the site, this is the stiffness. Okay? And so if we compare the joiner bore distance for the station and for the sites, we see the difference, right? So the station is about 2.7 kilometers from the fold, and the sites are as close as 45 meters to 2 kilometers. So the sites are closer to the fold, right? So therefore, assigning the recorded PGA to the sites might not be the best option, right? If we look at the VS30 or the site condition, the station is located on a site with 570 meters per second of VS30, while the sites are at softer locations. So there are also a difference here in site effects, right? The station is located at a stiffer site. So basically, this is to show that perhaps just taking the value that was recorded at this station might not be the best for these sites, okay? So now, with those pitfalls, I will show you what we used, and this is building on several developments listed here at the bottom. As I said, I will focus on PGA, but the similar approach was used for PGV and a couple other intensity measures. And so in essence, okay, before we go into some of the formulas and so on, in essence, let's say that we have a site like the one here on the right. This is the Alameda Bay site, and we want to know what was the PGA that we could have expected to record during the Loma Prieta earthquake in absence of liquefaction, okay? So what we are doing is basically we'll take all of the PGAs recorded in all the stations actually, but I'm showing here only a sample, those that have the stronger influence on this PGA. And we will inform a ground motion model estimate with those recorded, okay? So again, it's basically using the recorded PGA values near the site to inform a ground motion model estimate. That is, in essence, what we will be doing. And so I see here something on the chat, Scott.
Charlie just posted in the chat that if anyone has a question, feel free to post it in the Q&A feature at the bottom. Yeah. So nothing to do at this point. Remnant, keep going. I turned my camera on just so you have somebody, you know somebody's listening, right? It's awkward to do these.
Yeah, yeah, thank you. Thank you. Yeah, no problem. Okay, so so in essence, this is the method. We use the data that we have available to inform a ground motion model prediction. Now, if we go step by step, okay, there are 5 key steps. First off, let's compute residuals for a given earthquake. The residual is basically the difference in that recorded. I have IM here, it stands for intensity measure, but I'm focusing on PGA now, minus the log of the ground motion model, GMN, based estimate, okay? And so here is the explanation for the symbols, and I am showing here a view of the stations and case histories for the 1989 Loma Prieta earthquakes. The triangles are the stations, okay? So we have data there. We have a recorded PGA. And the circles are the case history size. This is what we care about, right? We have the station, that's great, but we care about the PGA at these circles. And so we can compute the residuals using this relation, and then we can correct those residuals by the event term, by basically removing the event term that we estimated as the average of all the residuals. Basically, given an earthquake, it might be the case that a ground motion model, on average, overestimates the values or underestimates the value. So the event term is basically accounting for that, for overall over or underestimation. And so here we now have the event corrected residuals or within event residuals, it's the same. And so I have those values at each one of the stations. The next step is Kriging interpolation, right? So now I will take all of those values at the stations, and using some correlation models, spatial correlation models, we can compute what will be that within event residual at the liquefaction case history sites, right? And that is what we care about. And so now that I have this, okay, I can take my within event residual at the circle locations, and I have to go back now, okay? I have this Kriging interpolation based within event residual. I add back the event term, and I have the estimated residual, and I can add this estimated residual to the ground motion model estimate, right? And so with this, I have finally my intensity measure, in this case, PGA, right? So again, I'm just using that residual to correct or to inform that ground motion model estimate. So a key step or a key component in all this process is the spatial correlation model used for a given earthquake. And we evolved throughout the project. We started using a more common or traditional frequentist approach for estimating these correlation models. We tried a few functional forms, but we noticed that the exponential was giving better fit to data. What I'm showing here is the semivariance, and the horizontal axis is the lag distance. So in simple terms, the vertical axis is showing the degree of similarity or dissimilarity between two locations with distance, okay? So basically, if two sites are, at 0 meters from the one another, then the dissimilarity is 0. And as the separation distance increases, then the dissimilarity increases, right? And so we were getting results like the one on the left. This is for the Chichi earthquake. It was making sense, but we also got some results like this on the right side. This is for an earthquake that did not lead to any liquefaction, but I picked it because it conveys the idea very clearly. The semivariance, the semivariogram model on the right side does not make a lot of sense. So we were not very happy with this. We realized that this may happen, not necessarily, but this may happen for cases, particularly with very few ground motion recordings, right? And those tend to be those earthquakes that happen at locations where there are no very dense seismic stations, and also perhaps old events, right? So it was a kind of a big problem because a lot of these legacy liquefaction earthquakes come from old events. And so at this point, we decided to shift towards a Bayesian approach, right? We kept the same exponential functional form. I'm showing again the estimated semivarograms for the Chichi earthquakes on the left. We can see now that we don't have a single model. We consider for the rest of the project 1,000 models, just as a balance between computational demand and a large number that addresses the uncertainty. And also, we are getting more meaningful results for some of those other, perhaps less recorded events. So we were happy with these results, but then we look at some of the maps that we were interpolating using these models. And so this is a map just following on the Loma Prieta earthquake. Again, you can see we have the stations, and we have the circles with the liquefaction sites. And all the colors are the interpolated within event residuals using those correlation models. And so what we see here is that perhaps we are defaulting to a mean value of 0. 0 is the kind of a white here in the middle of the color bar too rapidly. Okay, for example, here you see that we have a very dark blue color. And at this other station, we also have a very dark blue color. So those are two stations that underpredicted significantly the earthquake, the PGA. And in between, given that we don't have any other information, we would expect to have also some dark blue color, but we were defaulting or getting too rapidly close to 0. So that was not very satisfying. At this time, Professor Jack Baker published a paper by Lucas Bodenman et al. 2023, where they used also a Bayesian approach, but different functional forms. So instead of using the exponential model with a more rigid functional form, they had a couple of variables there free and consider those to be variables to be regressed using the Bayesian inference. And so I shifted here to a different way. Okay, this is not a semi-variogram again anymore. This is a correlogram, just correlation model, right? And in this case, it goes from 1, perfect correlation at very short distance or 0 distance, and then it decays, okay? And so Bodenman et al. Not only had a model based on Euclidean or spatial distance, but also an angular distance relative to the epicenter, okay? And so we use these models and we tried those again, and the results were better. I will show you in a minute, but before that, I want to mention a couple of things. This will come up later. These correlation models, some of them show a rapid fall off the correlation with distance. Let's say within the first kilometer, so 2 locations that are separated only 1 kilometer, may have a correlation that goes down to, I don't know, like 0.7 in this case. Okay, so that was also a little bit surprising. We expected that correlation to decay more smoothly, but perhaps that is given that we do not have a lot of closely spaced stations. Okay, so using these correlation models, we again computed the maps. In this case, the one on the left is the one that I had using the exponential model. The one on the right is using the models proposed by Bodenman et al. And we were more satisfied in this case. You see these 2 stations that I was pointing at before do not show that much of a rapid decay in between the locations. So we felt this was a good approach, a good model to continue our work. So with that, I want to also talk a little bit about the benefit of using this Bayesian approach and how important that was for our work. I am showing here, for example, a well-recorded event, okay? So let me provide some context. In the Bayesian framework, we set some priors for variables that are in the model, in the functional form. In this case, we have 3 variables. We have an exponential here. We have a correlation length for the Euclidean distance and a correlation length for the angular distance, okay? And so basically, we set these priors and then we update the distributions, the prior distributions, based on the data available, okay? And so basically, if we have a well-recorded event, like the 2011 Tohoku earthquake, we have in this case more than 500 recordings. Then these prior distributions here shown in blue at the top are kind of ignored, or not ignored, but updated heavily, right? The data that is used to compute these models will dominate over the prior distributions. And what I am showing here with this distribution, this is a little bit narrow, is the posterior distribution. So basically, those are the values that make sense based on the data available, okay? And so as you can see, there is a very narrow distribution for this parameter. That is because this is a very well-informed, well-recorded earthquake. But not all of the earthquakes are well-recorded. For example, here I have the same distributions, the prior and the posterior, for a poorly recorded event, right? This is a very old event, 1968, and we only had 5 recordings, right? So in this case, our posterior and the prior distributions are almost the same, right? At least you can see here for this exponent. We are not really informing much, or we are not very well informed with the data, so we keep the prior distributions. There is some more important change here for the angular correlation length. And so you can also see this a little bit more easily. If you look at the bottom plots, these correlation models really span a wide range of trends, right? And that is because we really don't have data to constrain these correlation models, okay? So it's convenient in that way. If we have a well-recorded event, then we inform the priors and we get a model that is very event-specific. If we do not have enough recordings, then we keep somewhat close to the priors and our models span a wide range because we do not know better. And here, just an intermediate case, again, the models for Loma Prieta earthquake. And so now we've talked about the issues and the pitfalls with the legacy PGAs. We've talked about the methodology used and the spatial correlation models. So now let's go ahead and see some results, okay? I will start with this comparison for the Loma Prieta earthquake. On the left side, you can see a plot. This is a one-to-one plot, I think it's called. Basically, what I show here in the horizontal axis is the PGA that we estimated in our work. And in the vertical axis, the legacy PGA, okay? We have here 3 lines. The one in the middle is the one-to-one line. If a point or a marker is on the one-to-one line, that means that our values and those from previous data sets or the legacy value are exactly the same. If the markers are below that line, our values are higher. If the markers are above the line, then the legacy PGAs were higher, okay? So we see it's hard to provide an overall conclusion. We don't see a trend, a systematic trend, but we can explain what happened one by one. And so I am showing here these markers based on the method used for the legacy PGA, okay? So now let's see what explains some of these differences. For method 1, and I am matching the color of the title of the method with the color here in the plot, we have a couple of them, okay? A couple of these cases were estimated, or the PGA was estimated based on the collocated recording. They are relatively close to the one-to-one line, okay? Now, one thing to note is that these PGAs were referred to as collocated, but in fact, the station was 200 and 500 meters away from the liquefaction site. So it's a little bit difficult to define what collocated means, right? But perhaps these are a little bit far away, particularly given that there is this drop in correlation that I mentioned before, right? Some of these events show a rapid fall in the correlation, even within the first kilometer, right? So that explains why the Alameda Naval Air Site has some difference between our values and those estimated in the past. This is the site that is 500 meters away from the station. Treasure Island is only 200 meters away. So for method 4, ground response analysis, again, is a little bit hard to assess. In general, they are close to the one-to-one line, except with these 3 sites that are, they have a low PGA, okay? The next one is method 5, nearest station. These are the sites in the most landing area. There are a number of case history sites in there. They are close to the one-to-one line. Of course, there is some difference expected because we're using a different method. But the most important difference is this one, the discrepancy with the Alameda Bay Farm. We have a value that is about 50% lower, okay? And so what happens is that the PGA assigned to this case history site was based on a station located 7 kilometers away, right? So if we saw some discrepancies just within the first kilometer, imagine 7 kilometers away, right? It will be hardly representative of the site conditions at the liquefaction site. So that explains why the important discrepancy. And finally, ground motion models. In this case, we see a trend. On average, our values are lower than those, are actually higher than the legacy PGAs. And we look into the differences in the models that were used. So method 6, again, is ground motion model. All of these legacy PGAs were estimated based on the Bohr et al. 1993 model. And we use the Bohr et al. 2014 model, so an updated version, right? And there are several differences between the models. For example, they did not use a VS theory as an input for side effects. They use some side categories. Of course, the data that we have is also, or the data that this researcher had to develop the 2014 model is much broader, so probably better informed as well. Those were the key differences in the models. And the other one is that the legacy PGAs did not consider the event term correction. And that makes for this Loma Prieta earthquake, about 10% difference. Okay, so now this is Loma Prieta. This is a figure, it's a little bit loaded. It's showing all of the results of the case histories. And so let's take a moment to see what this is showing. The axes are the same. Our PGAs in the horizontal axis and the legacy PGAs in the vertical axis. In this case, for Loma Prieta, there were only 4 methods that were used. In this case, we have the 7 methods that go from the co-located, interpolated, and so on. Okay. Again, one-to-one line. There is no clear systematic trend, right? They are all well above and below. We have in this case the 1-to-2 and the 2-to-1 lines. Before I had the 1.5 lines, and I am showing some of these markers with labels. Okay, I'm focusing on the ones that are farther away from the 1-to-1 line, because that will be interesting to see what led to such important discrepancy. Okay, so now let's look at this. Let's look at the ones that are showing an important discrepancy. First off, overall, the newly estimated PGAs vary from half to twice their legacy counterparts. So on average, there is a factor of 2, right? They are well within the 1-to-2 and 2-to-1 lines. If you take the average of all of these points, the difference is only 5%. Okay, the legacy PGAs on average are only 5% higher than our values. But of course, you see there is a lot of scatter. So let's go and see some of these cases. Method 1, co-located. The ones that I am explaining here are these 2, Bones Corner. On a Hama port, they show a significant discrepancy. Also, these sites in Niigata after the 1964 Niigata earthquake, and these other sites from the Kobe earthquake. And so basically, what happens is that all of these legacy PGAs were based on recordings that were affected by liquefaction. And therefore, we did not consider those recordings in our Kriging interpolation method. And here you can see some examples of those recordings. In this case, for example, you see the Bones Corner legacy PGA is twice the value that we estimated. And if we look at here, the Bones Corner, well, liquefaction was initiated or is observed somewhat early in the earthquake. And we have some of these dilation spikes that are perhaps exaggerating the PGA. And this is why it would be expected that the legacy value is higher, right? And a couple of other cases on the other side is the ones for Kobe. I believe, yeah, this is the Niigata. In this case, we have higher values, and you see here, well, the PGA or the initialization of liquefaction, again, is somewhat early in the earthquake, and then we have this over here and some very low accelerations. This is the recording, or this recording, this station was located at that building that tilted, that is presented in many liquefaction pictures from this event, and it's in Professor Kramer's textbook as well. So probably a lot of you have seen this picture or this building. So that explains the difference for this method. Let's go to method 2. This one was a little bit surprising because in essence, we are using the same methodology for estimating PGAs. You can see here some of these orange diamonds in the middle, and we have some important 5 cases where there is some important discrepancy. Those 5 cases correspond to the 2011 magnitude 5 Christchurch earthquake. This is an aftershock of the main event. And then we have some other important discrepancies, perhaps some of these that are somewhat far away from the 1-to-1 line that correspond to all these other earthquakes in New Zealand. And so after doing our detective work and looking at each one of these cases and what might be leading to this discrepancy, particularly given that we have used the same method, we found out that the reasons are the VS30 values that we used at the site. We estimated a VS30 at each one of the sites, while some of these legacy PGAs were based on maps of constant VS30, right? So that played an important role in this difference. The second is the ground motion database, particularly for this, I believe it's the tar field. Some of these earthquakes, we have a much larger ground motion database, so our estimates are better informed that way. And we also have some differences in the spatial correlation models. As I said, we use the models that just were published last year, Bodenman et al. And so that also contributes to some of the discrepancies. These are the key aspects. There are some other, for example, they use the geometric mean PGA, we use the ROD-D50, but that should not play that big of a role. I have now method 3. In this case are these crosses, okay? We only have 48 cases and most of them from the Kobe earthquake. And so by looking at how, so this is the map that was used to estimate a PGA for some of those legacy PGAs. And so there are 2 differences. First, that this station right here shows in this map a PGA of 0.5 Gs, while in our database, this station has a PGA of 0.3, and we cannot tell where the difference is coming from. Both components show a similar PGA around 0.3, and so we believe that the difference is probably in the ground motion processing, right? So that plays some role, but the most important one is that we do not have this recording showing a 0.33 Gs. We do not have this in our database, and so as you can see, all of these circles around this station are less informed than this map. Okay? So that is showing or leading to this discrepancy. Just the last one. This is the judgment, method 7. In this case, we have this discrepancy, important discrepancy for these sites in Sendai after the 1978 earthquake. We did not have enough recordings of that earthquake to apply our method. So these estimates are based on the Parker et al. NGA-SAP ground motion models. And when it comes to judgment, it is really hard to tell what are the underlying reasons for the discrepancies. Okay, so with that, I have shown you how these values compare to the legacy PGAs. And now the question is how that would impact the liquefaction triggering models. And this goes beyond the scope of my work, but I thought it would be interesting to show the effect. So this is on the left, the figure that I showed you at the beginning, the second slide. just in a different format. Okay, you have here at the bottom, and the horizontal axis is the resistance, and then the vertical axis is PGA. Okay, seismic demand represented by PGA. This is for the CPT database by Bull and Jay and Idris. And what we have on the right side is the same in terms of resistance, but we are plotting our PGAs. Okay. So as you can see, our values are a little bit compressed. They show lower PGAs compared to those by Bull and Jay and Idris. And the separability is a little bit lower. We proposed a separability index that varies from 0 to 1. If two data sets are perfectly separable, okay, if we have, let's say, all the red circles on this side and all the blue or white circles on this side, then the separability would be 1. If they are impossible to separate, like overlapping, then the separability is 0. Okay, and so what we have here is, based on the calculations, a separability index of 0.6 for the Bull and Jay and Idris CPT database, and we have a slightly lower separability index for our values. We decided to show this data in this way because, trying to separate these points would mean really developing a liquefaction triggering model. And there are some efforts going on that regard, but in this case, I'm just showing you this. Now, what this figure tells us is basically that refining the PGA or the seismic demand, more in general, does not really explain what led some cases to manifest liquefaction and some other cases not to do it. Okay. So let me see what I will do now, and keep an eye. There are some models coming up that have used these newly estimated PGAs. So I want to take a couple of minutes to talk about the DesignSafe dataset. So our project is PRJ 4022. We have 3 main products in there. The first product is the newly estimated PGA, as well as values for peak ground velocity, areas intensity, and cumulative absolute velocity at the liquefaction case history sites on the next generation liquefaction. Okay, so there are some CSV files that are very easy to access and read. The second product that we have is the spatial correlation models for most NGL earthquakes. I'm saying most because in some cases, some of those very old events that are either poorly recorded or we do not have any ground motion records at all, we couldn't really develop spatial correlation models for. So, but most of them have these models available. We have the maximum a posteriori model, which is the one in the Bayesian framework that explains better the ground motion data. And also, as I said before, 1,000 spatial correlation model realizations. The next product that we have is GM Kriging, an implementation, Python-based implementation that can be used for computing PGA and the other ground motion intensity measure at a site that you may want to know about, but it's not on NGL, right? So you have all of the ground motion intensity measures readily available at the liquefaction case history sites on NGL. But if you happen to be working for some other location or you have some other case history site of interest, you can use GM Kriging to compute the ground motion intensity measures. Okay, this is a summary of all of the cases that we have. So here in blue on the left side, for 30 events, we have spatial correlation models and Kriging interpolation-based ground motion intensity measures. These represent 86% of the case histories. And for another section, the remaining 14%, we have the ground motion intensity measures based on ground motion models only. You can find all of these values or the values for all of these events right now. And very soon, we will be posting some other values in the PRJ 4022 version 3 with some more ground motion intensity measures, all of these events. They seem numerous, but they only represent 4% of the liquefaction case history dataset. Okay? If you have questions about any of these, feel free to reach out. We're happy to provide some of these resources or guide you in their use. So with that, it's almost 1 hour here, Pacific time, so we'll conclude with some final remarks. First off, the newly estimated peak ground acceleration values, PGA, differ from PGAs used in the development of legacy liquefaction triggering models. This discrepancy is on average. It goes from 50% to 200%, meaning that the newly estimated PGAs could be as low as half the legacy counterpart or as high as twice, right? But on average, there is no systematic discrepancy, and there is only a 5% difference. Our values are on average 5% lower than the legacy PGAs. And the discrepancies really depend on event-specific or case-specific data, methods used, and so on. We've been doing a lot of detective work to figure out what is leading to these discrepancies, and there is really a wide range of reasons. It's hard to summarize as one reason leading to the discrepancy. The estimated PGAs show a slightly less clear separation of the liquefaction and non-liquefaction cases compared to the PGAs used by Bull and Jean Idris, specifically the CPT dataset. The lower separability suggests that PGA alone cannot explain the underlying mechanisms leading some sites to manifest liquefaction and not others. Okay, so there is probably more work to do in this regard. The correlation models developed for the PGAs and also some of the other ground motion intensity measures show a rapid fall-off in the correlation as separation distance increases within the first kilometer. So we were expecting that the correlation will remain a little bit high for perhaps a couple of kilometers and then smoothly fall off, but that was not the case. And this impacts the estimated PGAs at liquefaction sites near seismic stations, right? The discrepancy, if you have a liquefaction site near a station, might be a little bit higher than expected because of this rapid fall-off. The newly estimated PGAs are being used, as I said before, by the next generation liquefaction model teams to develop liquefaction triggering models. And finally, future research could focus on developing correction factors to enable the use of these ground motion intensity measures, alternative to PGA, like PGV, CAV, and areas intensity, in liquefaction triggering models, right? We have estimated these ground motion intensity measures, but we need some of these other components like the shear stress reduction factor, magnitude scaling factor, overburden, and so on, to be able to perhaps use this in a liquefaction triggering model, or perhaps some models can be developed that do not need those corrections. With that, I just want to acknowledge a number of people that contributed to this project. There is a long list here. And thank you. Run out of voice.
All right, thanks a lot, Renman. If you have questions, feel free to post them using the Q&A feature. There are a couple that have already come through. Renman, I don't know if you've looked at them, but I can read them out for you. So the first one says, thank you for your presentation. How does peak ground acceleration correlate with the occurrence and severity of liquefaction at various field case history sites, investigating the thresholds of PGA that tend to trigger liquefaction in different soil conditions? Then I think the third question is actually related. So that question is about how spatial variability within a site might influence the observed patterns of liquefaction within a large liquefaction zone.
That was a long question, Scott. Where can I read those questions? Let me see.
If you click on the bottom, the Q&A,
I don't. Oh, okay, there you go. Okay. So okay, so you said I should go from the top to the bottom, right?
well, it's the first and third one that are
Okay.
kind of continuations. The third one's kind of a continuation of the first one, right?
I see. So the first one, so it's talking about the severity. How does PGA affect liquefaction manifestation? So I haven't really looked at the cases that was not within the scope. I was just looking at the ground motion intensity measures. But I mean, I think not surprisingly, the higher the PGA, the more severe the liquefaction manifestation. But I don't know, Scott, if you, in your efforts in developing the liquefaction triggering model, have looked at some of these.
Well, I think with respect to the question about whether spatial variability of PGA is related to observations of liquefaction, I think we really don't know how spatially variable ground shaking is over those short distances, right? Like there's very few recordings that less than 1 or 2 kilometers apart from each other. And that's pretty big compared to most liquefaction sites. So I think that we do need some very closely spaced ground motions to constrain that part of the model. But yeah, I mean, we have looked at other intensity measures also, right? PGV and Areas intensity and so forth. And PGA and magnitude combined seem to work as well as those others.
Yeah, I mean, just to add, perhaps to put some context, the span of this liquefaction observation sometimes can be, I don't know, a few hundred meters, right? But our stations, I mean, we have the model, right? The spatial correlation model looks continuous, but we only have very spaced recordings, right? Perhaps a spacing of 5 kilometers, 2 kilometers. We have very few within 1 kilometer. So it's really, as Scott was saying, it's really hard to assess with what the effect is.
Yeah. So
Yeah.
there's one more question, Rinman. Maybe we can answer that one quickly since we're a little bit beyond time. The question is, why did you limit the x-axis of your semi-variogram plots to 50 kilometers?
Oh, yeah. So that was basically, that's an important point. We have developed these spatial correlation models and have done all of these calculations specifically for liquefaction case histories. And so we basically computed the distance, the RJB or joiner bore distance in the case of crustal earthquakes for all of the liquefaction case history sites. And I think more than 95% of them fall within the 50 kilometers. So this is why we limited the data that we use to only 50 kilometers. That's an important point. If we want perhaps to use some of these models for other applications, they might not be as applicable. This is why when I was showing some of those well-recorded and poorly recorded events, I mentioned what I had in the text is in the context of this work, right? We may have more recordings, but after leaving aside those beyond 50 kilometers from the full RJB, then we had only a few left in some cases.
All right. And then there's one more question that came in. Maybe this will be the last one. I want to give you a chance to answer it because it's about site response, which was the topic of your PhD, right? So
yeah,
work with Katarina and Norm and so forth at Davis. So in method 4, ground response analysis, what software did you use for the analysis?
Oh, so yeah. So I love ground response analysis, but I didn't get to do it with this project. The ground response analysis, the method for those were legacy values. So I basically took the values that some other researchers computed in the past and compared those to the values that I computed using the method that I showed. In terms of software, well, they use Shake 2000 or some variant of that. These are legacy PGAs, so most of them were estimated, early 2000. So I'm guessing Shake 2000 was predominantly what they used.
Yeah. Thanks a lot, Raymond. Thanks for being here today.
Thank you.
Hand it back off to Charlie to close it out.
Thank you. Thanks, everyone.
Great presentation, by the way, Redmond. Thank you so much for sharing this. As some people have asked, let's get this. As some people have asked, this will be curated by our marketing. If you can all see my screen, I think. Yeah, it looks like it. Yeah,
we see it.
Our marketing department will be curating the video, and as soon as that video is available, it will be posted to our training channel. The training channel can be reached by this URL, designsafeci.org Learning Center, or go to the top menu of DesignSafe, click on Learning Center, and you'll see where the training archives are and news of any upcoming training that's being done. Once again, we really appreciate your feedback. So there's a QR code for that feedback again. Please let us know how this webinar went. Please let us know if you have any suggestions for future webinars and how these webinars are feeling for y'all. Really appreciate everyone's time. Really appreciate everyone's effort on this. Thank you so much. And once again, thank you so much, Redmond. And congratulations on being one of the DesignSafe Data Award winners. We really appreciate your time and commitment to DesignSafe and helping build our community. So thank you. And of course, thanks again, Scott. And thank you, Natalie. Everyone, appreciate your time. You all have a great afternoon, and we'll see you next time. If there's any other questions, feel free to reach out to us on Slack. All right. Thanks, everyone. See you all next time.
Bye, everyone.
Bye. Thanks, everyone.